Hello there, welcome to a journey across time, to the very beginning of our planet's story. Imagine a world of fire and molten rock, where oceans had yet to form and the air was thick with clouds of vapor. This is the Hadean Eon, the fiery cradle of Earth where chaos and destruction ruled, and yet, from this seemingly inhospitable world, the first sparks of life began to emerge. Join us as we explore how our planet transformed from a molten wasteland into the thriving world we know today. Imagine a time so distant that it stretches the limits of human imagination, a time not measured in centuries, not in millennia, not even in the familiar cadence of history that speaks of empires and civilizations. Instead, we must measure it in billions of years. 4.5 billion years ago, long before the first forests, before the first animals, before even the faintest spark of life shimmered in the oceans, our planet was born. This was the Hadean Eon, the very first chapter in Earth's story. Named after Hades, the Greek god of the underworld, the name itself conjures images of fire, chaos, and desolation. And indeed, the Earth of this era was no paradise. It was a raw, violent, and alien world, yet it was here, amidst the searing heat and endless bombardment, that the foundations of our modern planet were laid. The human imagination versus deep time. When we talk about billions of years, the human mind struggles. We are creatures of short memory, accustomed to measuring our lives in decades. The rise and fall of civilizations, from the Egyptian pyramids to the digital age, is but a flicker compared to the age of the Earth. To even begin to imagine that Hadean is to step beyond the limits of human history and into the grandest of all scales. Deep time. If all of Earth's history were compressed into a single year, with January 1st marking the planet's birth and December 31st representing the present moment, humans would not appear until the very last few minutes of December 31st. Dinosaurs themselves would have appeared only in late December. The Hadean, by contrast, would occupy nearly all of January, the very beginning, when the calendar of Earth was just opening. Birth from chaos in that opening month. Earth did not resemble the blue and green marble we know today. Instead, it was a churning sphere of molten rock, constantly reshaped by collisions with planet-sized bodies drifting through the young solar system. The sun itself was young and restless, radiating solar winds and energy with far greater intensity than today. The planets were still forming, their orbits unstable, their futures uncertain. The Earth's birth was violent. From a disk of cosmic dust and gas orbiting the infant sun, countless particles collided and clumped together, gradually forming larger and larger bodies. Over millions of years, these bodies grew, and through gravitational attraction, they slammed together with unimaginable force, generating enough heat to melt rock itself. What emerged was a molten, glowing Earth, wrapped in a haze of vaporized rock and metal. And yet, amidst this destruction lay creation. Each violent collision, each molten tide, and each wave of cosmic energy contributed to shaping the planet that would one day cradle oceans, mountains, forests, and life itself. The curtain rises when we use the word Hadean. We are not speaking of a place humans could have walked upon. There were no continents as we know them, no oceans in which fish could swim, no atmosphere to breathe. The Earth of the Hadean was a world of extremes, seas of molten rock, glowing under a darkened sky, atmospheres of toxic gases, heavy with carbon dioxide, methane, ammonia, and sulfur, unending bombardments, as asteroids and comets rained down, each impact capable of reshaping entire regions of the planet's surface. Temperatures soaring above 1,000 degrees, hotter than the vents of today's volcanoes. It was an Earth that seemed utterly inhospitable, and yet, it was here that the essential ingredients of habitability began to take shape. The paradox of beginnings. One of the great paradoxes of the Hadean is that even in the midst of such destruction, the seeds of stability were being sown. It was during this eon that the moon was born, ripped from Earth's body after a titanic collision. It was here that the first crusts of rock cooled and solidified upon the molten surface. It was here that the first raindrops may have fallen, hissing as they struck the steaming ground. And it was here, possibly, that the chemical building blocks of life itself began to gather. To look back upon the Hadean is not to witness an unbroken hell, but a story of transformation, for in every eruption, every impact, and every collapse, the Earth was moving step by step toward becoming the planet we know today. Why the Hadean matters, one might ask. Why should we care about a time so far removed from us? After all, no fossils remain from the Hadean, and no ancient landscapes survive intact. What value is there in reconstructing this lost, infernal world? The answer lies in perspective. The Hadean is not simply a forgotten chapter. It is the opening act of the greatest story ever told, the story of life. Without understanding the conditions of Earth's earliest days, we cannot fully appreciate the resilience of life, nor the fragility of the environment that sustains it. Studying the Hadean allows us to glimpse not only how planets form, but how worlds perhaps even beyond our solar system may become habitable. In the Hadean, we see the struggle between chaos and order, between destruction and creation. It is, in many ways, a mirror of the universe itself. The journey ahead in the chapters to come, we will descend deeper into this ancient past. We will witness the Earth's fiery birth, the cataclysmic impact that gave rise to the moon, the storms of rock and ice that bombarded the surface, and the slow emergence of oceans and atmosphere. We will examine the minerals that carry whispers of this forgotten age, and the chemical reactions that may have set the stage for biology. The Hadean is not merely a scientific curiosity, it is the crucible of existence, the forge in which the elements of life were first assembled. So, let us step across the threshold of time. Let us travel back to the very first days of Earth, when the planet was young, raw, and untamed. The curtain rises, the stage is set, the Hadean begins. Birth of a world, from dust to their impact fade in darkness strewn with stars. In the distance, a pale fire stirs. The newborn sun its breath, a gale of charged particles sweeping a vast, swirling plain of gas and dust. The cold beginning, a cloud and a spark long before oceans boiled upon a molten earth. Long before continents rose and broke like rafts of stone, there was only a molecular cloud, a frigid tangle of hydrogen, helium, and dust grains infused with heavier elements, forged in ancient stars. Here, at 10 or 20 degrees above absolute zero, chemistry idled and time seemed to stand still. But gravity was at work, and gravity does not rest. A passing shock, perhaps, the death cry of a supernova compressed a region of this cloud until it collapsed under its own weight. As matter rushed inward, angular momentum forced it to flatten into a protoplanetary disk around the forming sun. The center ignited, light poured forth, and in that flattened disk where temperatures and pressures changed with recipe for planets spread out like concentric rings in a cosmic bakery. Close to the sun, where heat was fierce, metals and silicates survived. Farther out, where it was cooler, ices could persist. The inner disk would become the realm of the rocky planets. The outer disk, home to giants and their icy retinues. Earth's story begins here, a ring of warm dust, stirred by turbulence, threaded by magnetic fields, bathed in sunlight, and haunted by the twin sculptors of destiny, gravity and collision. Dust to pebbles, the first steps toward a planet at scales invisible to any eye. Dust grains bumped, stuck, and clumped. Electrostatic forces lent a helping hand. Fractal aggregates formed, delicate as snowflakes. In the disk's gas, these clumps drifted inward, concentrating along pressure ridges like leaves gathering in an eddy. Where the traffic jammed, density spiked. Pebbles, objects millimeters to centimeters across, became common. The leap from pebble to mountain is not a single bound, but the disk had a trick, streaming instabilities. Where pebbles were dense enough, their collective drag on the gas slowed them, drawing more pebbles into the same flow, thickening the traffic until gravity could seize the crowd. In sudden collapses, planetesimals, bodies kilometers to hundreds of kilometers across, condensed out of the churn like hailstones, condensing from storm clouds. These planetesimals were the true seeds of worlds. Their gravity, small but real, bent pebbles into spiraling paths and drew other planetesimals into long, dangerous dances. When they collided, they merged or shattered. When they survived, they grew. Runaway and oligarchs, the hierarchy of growth in the early solar system was biased toward the lucky and the large. A slightly bigger body has a stronger gravitational pull. It sweeps a wider path. It eats more. This positive feedback created a phase called runaway growth. The big got bigger, fast. In each neighborhood of the disk, a few bodies surged ahead, carving up the local supply. As time passed and the neighborhood thinned, growth entered the oligarchic stage. Each regional heavyweight oligarch ruled a broad swath of the disk, shepherding or swallowing smaller neighbors. Collisions were common, so were near misses, deflections, and captures. The inner solar system became a crowded arena of stone and metal where a dozen or so embryo planets, Moon to Mars-ized, circled the sun on orbits that occasionally crossed. Some embryos boasted iron-rich cores already, their interiors melted by a trifecta of heat sources: gravitational energy, released during accretion, Radiogenic heat from short-lived isotopes, notably aluminum-26 and iron-6, impact heating from relentless collisions. The consequence was differentiation. Dense metallic iron sank to form cores. Lighter silicates floated to form mantles and crusts. Even in these embryonic days, the architecture of a planet core mantle, crust was being assembled. Heat and hell. The magmotion Earth lettuce, one embryo in the inner disk, gathered strength. Its growth crossed a threshold. Impacts came faster and harder. Each large collision reset the surface, pooling seas of liquid rock that shimmered like blood-orange glass under a black sky. The world in progress was a magma ocean planet, its skin solidifying in brief interludes, before the next blow shattered and remelted it. Within this incandescent body, iron percolated downward through the silicate melt, coalescing into a core. The sinking metal dragged cidophile elements, iron-loving elements like gold and platinum with it, depleting the mantle. Chemistry imprinted a signature the Earth would carry forever. Above this inferno, an atmosphere flickered in and out of existence. Silicate vapor after impacts, steam and carbon dioxide from outgassing, a haze of sulfur species from volatile-rich impacts. Gravity kept much of it close. The young sun's fierce ultraviolet light stripped some away. The surface boiled, the sky glowed. This was pre-Earth, a crucible in which the Hadean would soon begin. The last and greatest collision, this arena of giants. Orbits were not stable for long. Perturbations from Jupiter tugged at the inner system. Resonances nudged embryos into crossing paths. And then, one day, if days meant anything in such a time, Mirth's path intersected with that of a rival. Theia. We name it now. But to the cosmos it was simply another world, likely Mars-sized, differentiated, warm, and doomed to change history. The collision that followed was oblique, a glancing strike rather than a head-on catastrophe, and it unleashed energies that defy metaphor. Mountains vaporized. Oceans of rock lofted into the sky. The impactor itself merged and shattered, its core sinking toward Earth's own, its mantle torn into a ribbon of incandescent debris. This is the giant impact hypothesis for the Moon's origin. In the immediate aftermath, Earth was cloaked by a disk of molten and vaporized rock, some from the impactor, some from Earth's mantle, all trapped within the gravity well of a wounded, spinning planet. Inside the Roche limiter, few Earth radii from the surface tidal forces forbade clumping. Outside it, droplets and boulders coalesced into moonlets, then merged again, accreting the moon. Birth of the moon, disk, rain, and the skies above the incandescent Earth, an arc of glowing debris tracing the horizon, falling as rock rain while the outer disk gathered into a companion world. The process may have been faster in the order of months or years for the initial moon to assemble from the outer disk, followed by a long tail of accretion as inner debris migrated outward and merged. As the disk cooled, vapor condensed to droplets. Droplets collided and stuck. Boulder-sized clasts became moonlit. Gravitational shepherding, resonant tugs, and repeated mergers built the lunar body. Its early surface, too, was a magma ocean. Light plagioclase crystals floated and crystallized into an anathesitic crust, the pale highlands still visible today. Meanwhile, Earth spun rapidly, possibly with a day only a few hours long. Tidal friction between Earth and its newborn moon stole angular momentum from Earth's rotation, flinging the moon outward while lengthening the day. In time, the moon became the steadying hand at Earth's shoulder, damping wild swings in axial tilt and softly moderating the planet's long-term climate. Why a moon matters. A large moon is more than a nightlight. It is a metronome for planetary rotation and a stabilizer for axial tilt. Without it, Earth's obliquity might have wandered, chaotically driven by gravitational nudges from other planets. With it, the tilt oscillates within a modest range, shaping seasons but not lurching into climatic extremes that could have throttled the continuity of surface oceans or early habitability. Tides sculpted shorelines and stirred the young oceans that would later collect. They accelerated chemical exchange between rock and water. They may even have paced prebiotic cycles on tidal flats and in coastal pools. None of this required life yet, but it prepared the stage. A world reforged. Differentiation after Thiath impact that birthed the moon also reheated Earth. Much of the mantle melted again, some fraction vaporized, the core augmented by iron from Theias. The dulled mantle reservoirs mixed, then began to separate as the planet cooled. Heavy metal droplets rained downward through the molten rock, like glittering storms, releasing heat as they sank. Convection roared. The planet's interior organized itself. As the magma ocean crystallized, early minerals segregated. Dense crystals sank, lighter ones floated. Chemical gradients formed that would drive mantle plumes, volcanism, and crust formation for eons. Above a roiling atmosphere of steam, carbon dioxide, nitrogen, and sulfurous gases thickened from outgassing and from volatile-rich impacts that followed. The first atmospheres here and gone before the giant impact. Earth may have had a primary atmosphere captured from the solar nebula rich in hydrogen and helium. If it existed, the giant impact probably blew it away. The sun's radiation would have stripped what remained. What followed was secondary gases exsolved from the melting mantle, plus contributions from comets and volatile-rich asteroids that continued to arrive. This atmosphere was nothing like our breathable air. It likely teemed with water vapor, carbon dioxide, and nitrogen, with trace methane and ammonia in localized, reducing pockets. Lightning crackled through volcanic plumes. The upper atmosphere sizzled under ultraviolet light. Iron rained from meteoritic dust and rusted in ephemeral pools. With every eruption and every impact, the composition shifted a restless sky above a restless world. The clock of deep time. How do we place these scenes on a timeline? The cosmic clock begins with calcium-aluminum-rich inclusions, KAS, the oldest solids in the solar system dating to about 4.567 billion years ago. Earth's main accretion likely spanned the next few tens of millions of years. The moon-forming impact, judging from geochemical clocks that track tungsten and hafnium isotopes, and from ages of ancient lunar rocks, likely occurred very early in Earth's history, within the first approximately 50 to 100 million years after the exact date is debated, but its immensity is not. What matters for our story is the sequence. Disk gives planetesimals, gives embryos, gives collisions, gives Theia gives. Moon gives magma, ocean Earth gives cooling and outgassing. By the close of these events, the planet had a core that could power a magnetic field, a mantle primed for tectonics, a stabilizing moon, and an atmosphere heavy with steam. Hellish, yes, but also ready. Afterglow. The cooling of a magma world. No impact lasts forever. Even planet-sized scars heal. As Earth radiated heat into space, a rigid lid began to congeal atop the global or near-global oceans of magma. This crust was not the granite of continents. It was dark basalt, fragile and thin. Cracks rifted it, plumes punctured it, impacts perforated it, but each time it resealed a little thicker. It bought time for the surface to cool. When steam condensed, rain fell first as storms that turned to vapor upon hitting searing rock, then as deluges that lingered. Water pooled and lowlands seeped into fractures and interacted with fresh basalt, leaching elements and driving hydrothermal chemistry. True global oceans may have required repeated cycles of cooling and reheating, but the trend was set. The scalded planet was on a path toward liquid water. Variations on a theme, not just one. Impact scientists have proposed alternatives and refinements to the classic Theia scenario. Some models invoke hit-and-run collisions, multiple smaller impacts, or even a synestia fleeting bagel-shaped cloud of partially vaporized rock from which both Earth and Moon condensed. These ideas differ in geometry and in how much Earth versus impactor material ends up in the Moon. But they share a core truth. The final step of Earth's assembly was violent and world-defining. In all variants, Earth emerges, reorganized, and reset, with a newborn moon drifting outward and a mantle primed for the next act of planetary evolution. The scene set for the Hadean Eon, the time the debris fog cleared and the glow of the magma oceans dimmed. Earth stood recognizably itself, a differentiated planet with a metallic heart, a silicate mantle, a fragile basaltic skin, a thick hot atmosphere, and a bright companion circling close. The Hadean Eon, traditionally spanning Earth's first half-billion years, now begins in earnest. That is a time often caricatured as unending fire and brimstone, yet it is also the age of firsts. The first crust to persist for more than a geologic blink. The first sustained oceans on the surface, even if intermittent at the start. The first weather that lasted longer than an impact storm. The first geochemical cycles, water-rock reactions, carbon sequestration in newly formed minerals, and heat engines powering convection. The opening act has given way to the first movement. Earth is still raw, but it now has the tools with which to tame itself. A word on evidence, reading ghosts in stone. How do we know any of this? The Hadean left few direct rocks on Earth's surface. The planet's youth was too hot, too dynamic, but clues abound. Lunar samples from missions and meteorites preserve the fingerprints of an early lunar magma ocean and a violent birth. Isotopes in Earth's mantle and in ancient minerals capture the timing of core formation and the mixing and separation of reservoirs. Astrophysical observations of disks around young stars show that planet building is not rare, but common, and that collisions on a grand scale are a fact of planetary life. From these fragments, a coherent story emerges. Earth was assembled by gravity, sculpted by collision, and stabilized by the moon. Curtain to the next act, the lights dim on the era of formation, and rise on a stage of molten plains, black basalt rafts, steam-choked valleys, and skies torn by lightning. Impacts still fall, sometimes titanic, but between them, the planet breathes. Water gathers, rock reacts, heat flows from within. The Hadean is ready to unveil its paradox, a world both hellish and hopeful. The first surface, magma, oceans, crust, and the struggle for stability. The Earth has survived its violent birth. The moon now orbits as a glowing sentinel. The planet spins rapidly, its day only a handful of hours long. But beneath that sky of vapor and fire, the surface is still a churning, alien HELLSCAPE. The magma ocean, Earth. In the wake of the Theia impact, Earth was a sphere wrapped in oceans of molten rock. Vast seas of magma stretched from pole to pole, glowing a dull orange against the darkness of space. Temperatures soared above 2000 degrees Celsius, hot enough to melt silicate minerals, hot enough to keep metals mobile, hot enough to drive away anything resembling stability. From orbit, this infant Earth would have glowed like a small star. Clouds of silicate vapor and steam billowed outward, temporarily obscuring the surface. Raindrops of molten rock condensed in the upper atmosphere and fell back as fiery storms. The crust that tried to form was thin and fragile, constantly breaking and sinking back into the molten mantle. This was not a planet of land and sea, but a world where stone flowed like water and continents were a dream yet to come. Cooling the furnace, but even the hottest furnace cools with time. The Earth radiated heat into space relentlessly, and within tens of millions of years, the surface began to solidify. Cooling was not uniform. In some places, rafts of solid basalt floated, only to be swallowed by convecting magma. Elsewhere, impacts from asteroids reheated the crust, punching holes that bled fresh lava across the surface. Scientists believe that within 50 to 100 million years, Earth's outer layer began to stabilize enough that a protocrust could persist. This crust wasn't like today's continents. It was thin, dark, and fragile, composed mostly of basaltic rock. Think of it as a skin stretched over a still molten body, cracking and healing again. Above it hung a thick, choking atmosphere, steam, carbon dioxide, sulfur, methane trapped by gravity and released through constant the first continental seedsavon. In this chaos, something remarkable began to happen. As the magma ocean crystallized, certain minerals behaved differently. Light feldspars floated upward, forming buoyant islands of rock more resistant to sinking. These may have been the seeds of continental crust, small proto-continents that rose above the dark basaltic seas that they would not have resembled today's continents. They were tiny, scattered patches, perhaps no larger than islands, constantly under siege from impacts and lava flows, yet their presence marked a profound shift. The Earth was already beginning the long process of building continents. Even in the depths of the Hadean, some scientists point to zircon crystals, tiny, durable minerals dated to about 4.4 billion years ago, as evidence of these early continents. Found in Australia, these zircons are older than any known rock. Their chemistry suggests they formed in the presence of liquid water and continental-like crust. In other words, even while Earth looked like hell, oceans and crust were already forming. The cycle of destruction, yet nothing in the Hadean lasted long. This was an era of constant destruction. Asteroids and comets pounded the surface, some large enough to remelt entire regions. Volcanoes erupted endlessly, pouring lava into every lowland. Tectonic-like processes may already have stirred the crust, breaking and recycling it into the mantle. Every attempt the planet made at stability was undone, but with each cycle of destruction and renewal, Earth inched closer to becoming habitable. The first oceans of water. As the atmosphere cooled, the steam released by volcanic outgassing began to condense. At first, raindrops evaporated before hitting the molten ground, but as the crust thickened, water collected. Torrential rains fell for thousands of years, filling low basins with boiling seas. By around 4.4 to 4.3 billion years ago, evidence suggests Earth had stable bodies of liquid water, not oceans as we know them, but vast, shallow seas where heat and chemistry mingled. Into these waters fell minerals, metals, and organic compounds delivered by comets. Here, on this fiery young Earth, the stage was set for the greatest mystery of all, the origins of life. An atmosphere in flux. The atmosphere above these waters was alien. Carbon dioxide was the dominant gas, making the air thick and suffocating. Methane and ammonia drifted in from cometary impacts, reducing environments in pockets. Nitrogen, stable and inert, already existed in abundance, forming the background gas, much as it does today. This atmosphere trapped heat like a greenhouse, keeping Earth's surface warm despite the fact that the young sun shone 25 to 30% dimmer than it does today. This paradox, how Earth stayed warm with a faint young sun, remains one of science's enduring puzzles. The likely answer is that greenhouse gases created a thermal blanket, holding in the heat and preventing the planet from freezing. A paradoxical world. The Hadean Earth was a paradox, a planet battered and burned by impacts, yet already hosting liquid water, a world where skies rained fire, yet also rained water, a surface scarred by destruction, yet sowing the seeds of continents and chemistry. It was a planet both alien and familiar. If we could stand there, protected by some magical suit, we might glimpse the faint shimmer of the first seas under skies choked with storms, hear the hiss of rain on lava, and feel the tremor of impacts that shook the ground without warning. Evidence in stones, because almost no Hadean rocks survive. Our knowledge comes from fragments, tiny zircons, a handful of ancient isotopic signatures, and the battered face of the moon, which preserves scars of the same bombardment Earth endured. These fragments tell us water existed early, crust was already forming. The surface was not an unbroken hell, but a dynamic system, cooling, cracking, and renewing. The picture is incomplete, but it shows us an Earth already on its way to habitability. Setting the stage. The curtain is almost ready to rise on the next act, the late heavy bombardment, when Earth was pummeled by impacts large enough to vaporize oceans and sterilize the surface repeatedly. Yet even through these apocalyptic events, the crust reformed, the seas returned, and the chemistry of life crept forward. The Hadean was never static. It was a world in motion, a forge where destruction and creation danced together. Atmosphere and climate, fire, steam, and the first rains. The Earth, newly born, had a face of molten rock and seas of lava. But above that surface hung an atmosphere unlike anything we know today. It was a sky of poison and fire, a veil of steam and smoke, thick enough to trap heat, yet fragile enough to be reshaped by every eruption, every impact, and every storm. The vanished first breath. When Earth first formed, it likely captured a primary atmosphere from the solar nebula: hydrogen, helium, and traces of noble gases. But such gases are light, and Earth's early gravity was not enough to hold them against the assault of the sun's young, furious winds. Within a short time, perhaps only a few million years, this primordial atmosphere was stripped away into space. What followed was not borrowed from the nebula, but forged from Earth itself. Gases released from the molten mantle in an ongoing process, called outgassing, the breath of volcanoes. Imagine the planet as a vast cauldron, its mantle seething, its crust cracking and erupting endlessly. Through these fissures poured volcanic gases, water vapor, HO released in staggering amounts, enough to eventually fill entire oceans. Carbon dioxide, CO, thickening the air, trapping heat, and creating a greenhouse cloak. Nitrogen, N, accumulating as a stable, inert background gas. Sulfur compounds, SO, HS, lending the skies a choking acrid odor and forming hazes. Methane and ammonia, Shane, NH, occasional localized contributions from deep chemistry and cometary impacts. The air was dense, heavy, and hostile. To breathe it would have been to suffocate instantly. Yet in its toxicity lay promise. These gases were not just poisons, they were ingredients for chemical reactions that, one day, would weave together the first threads of biology. The faint young sun problem. One of the great mysteries of early Earth is the faint young sun paradox. Astronomical models tell us that the sun, in its youth, shone about 25 to 30% dimmer than today. If Earth had the same atmosphere it does now, its surface would have been frozen solid. And yet, geological evidence suggests liquid water flowed on Earth by 4.4 billion years ago. How could this be? The answer lies in the greenhouse cloak. High levels of carbon dioxide and possibly methane trapped heat so effectively that the surface stayed warm despite the weaker sun instead of ice. Earth had oceans that boiled, steamed, froze, and reformed under a sky that constantly shifted between chaos and calm. A sky of fire. The atmosphere was not still or gentle. It was a theater of violence. Lightning ripped through thick clouds. discharging energy into a soup of methane, ammonia, and steam. Each flash may have forged simple organic molecules, precursors to amino acids. Volcanic plumes towered high, filling the sky with sulfurous ash and droplets of acid. Meteor impacts punched holes in the atmosphere, briefly ejecting gases into space and then resealing them with shockwaves. Solar ultraviolet light split molecules apart, creating radicals that recombined in strange new forms. This constant chemistry meant that the atmosphere was not static, it was alive with reactions. A giant laboratory churning with the raw materials of future life. The first rains as Earth cooled. Steam condensed into rain. At first, raindrops sizzled into vapor the instant they struck the hot crust, but as cooling advanced, some drops lingered, then puddles formed, then rivers, then vast torrents of rainfall drenched the planet in storms that may have lasted thousands of years. Picture this, the entire Earth under endless thunderstorms, rain falling in sheets, lightning splitting the skies, floods carving the fragile crust. The first seas gathered in low basins, boiling at their edges, steaming at their surfaces, but persisting nonetheless. These were the primordial oceans, the basins where chemistry would soon mix rock, water, and atmosphere into something entirely new. Climate of extremes. The Hadean climate was not stable. It shifted with impacts, with eruptions, with changes in atmospheric chemistry. At times, the planet may have been hot enough to sterilize oceans, boiling them away into vapor after a massive collision. At other times, volcanic activity may have released cooling aerosols, briefly chilling the skies. But on the whole, Earth was warm and wet, wrapped in a greenhouse blanket. Temperatures may have hovered well above the boiling point of water at sea level, though high atmospheric pressure could have kept liquid oceans from fully evaporating. This climate unbearable to us was paradoxically the cradle of habitability. Cycles begin with atmosphere, water, and crust interacting. The first geochemical cycles were born. Rain dissolved minerals in basalt, carrying ions into the oceans. Carbon dioxide reacted with silicate rocks, beginning the long carbon cycle that still regulates Earth's climate today. Heat drove convection in the mantle, powering volcanic activity that recycled gases back into the air. These cycles were primitive and unstable, but they marked the start of Earth's feedback systems, the mechanisms that, over billions of years, would balance the atmosphere and allow life to thrive. A world of possibility, though alien and toxic. The Hadean atmosphere was not an obstacle to life, it was an incubator. The very gases that poisoned human lungs were the building blocks of amino acids, lipids, and nucleotides. The lightning storms that split the skies were sparks for chemistry. The rains that flooded the land carved out environments where molecules could concentrate, react, and evolve. Dot in the thick haze of steam and carbon dioxide. Under skies red with volcanic dust and black with storm clouds, the Earth was not just hostile, it was pregnant with potential. Looking ahead, the atmosphere and climate of the Hadean were the canvas. Onto this canvas, cosmic artists would soon fling meteors, asteroids, and comets in a storm of bombardment that scarred both Earth and Moon. This was the late heavy bombardment, a rain of fire from the heavens that threatened to erase the oceans and sterilize the crust again and again. And yet, through this destruction, Earth endured. Water returned, atmosphere replenished, chemistry advanced. The great bombardment, fire from the skies. The Hadean world was already a place of violence, lava, volcanoes, storms. But now came a new fury, not from within Earth, but from the depths of space. A storm of rock, metal, and ice, the scale of which defies imagination, swept across the inner solar system. This was the late heavy bombardment, a time when the skies rained fire, when oceans boiled away, when continents cracked, and yet, paradoxically, when Earth may have been seeded with the chemistry of life. What was the late heavy bombardment? Roughly 4.1 to 3.8 billion years ago, the solar system entered a period of chaos. Giant planets, especially Jupiter and Saturn, likely shifted their orbits slightly, disturbing the balance of smaller bodies in the asteroid and Kuiper belts. Millions of rocky fragments, icy comets, and metallic asteroids were flung inward toward the terrestrial planets. Earth, Moon, Mercury, Mars, and Venus all endured a relentless hailstorm of impacts. On the Moon, this era left scars we still see today, the great lunar basins like Imbrium, Oriental, and Nectaris. On Earth, almost no direct evidence remains. Our active geology recycled the crust many times, but indirect evidence from zircons and isotopes tells us this bombardment was real and transformative. The scale of destruction, imagine a rock 10 kilometers wide striking Earth at 20 kilometers per second. The energy released would be equivalent to millions of nuclear bombs detonating at once. Now imagine not one, but thousands of such impacts over hundreds of millions of years. These collisions boiled oceans into vapor, creating steam atmospheres, melted the crust, turning large areas back into magma seas, vaporized rocks, sending mineral vapors into the air that later rained down as molten droplets, ejected debris into orbit, some of which may have formed temporary rings around Earth. For long stretches, Earth may have seemed uninhabitable, an endless cycle of devastation. Yet after each impact, water condensed again, oceans reformed, and life's chemistry had another chance to begin. The moon is a witness because Earth's early crust was destroyed and remade repeatedly. Much of its direct evidence of bombardment is gone, but the moon preserves the scars. Its Great Maria and basins are silent witnesses to the storm. By dating moon rocks returned by Apollo missions, scientists determined that many of these basins formed between 3.9 and 4.0 billion years ago, suggesting a spike in impacts the heart of the late heavy bombardment. The moon, then, is not just Earth's companion, it is also a history book, keeping records of a chapter Earth itself erased. The dual role of bombardment at first glance. The bombardment seems purely destructive, but it had two faces: destructive force, sterilizing events. Impacts may have repeatedly wiped out any fragile proto-life that tried to establish itself, resetting chemistry. Oceans boiled away, molecules shattered, and surface niches destroyed. Creative force, delivery of water. Comets and icy asteroids may have replenished and enriched Earth's oceans. Delivery of organics. Complex carbon-based molecules, formed in deep space, could have been deposited in abundance, providing energy. Impact shocks created high-pressure, high-temperature environments that can forge new chemical bonds. Thus, bombardment may have been both a trial by fire and a gift of raw materials. The boiling oceans. One of the most dramatic consequences of large impacts was the repeated vaporization of oceans. When a massive asteroid struck, the released energy boiled entire seas into thick steam clouds. For thousands of years, Earth may have been wrapped in a global ocean of vapor, but as the atmosphere cooled, rains returned, and oceans condensed. Once more, this cycle of destruction and renewal may have happened multiple times, each cycle remixing the chemistry of the oceans, perhaps driving the complexity of prebiotic molecules further. Geological clues from zircons. While most evidence of bombardment vanished, tiny crystals called zircons, some as old as 4.4 billion years, have survived. These zircons show signs that liquid water existed even during the bombardment era. This suggests that Earth's oceans were never completely gone for long between impacts. Conditions stabilized enough for water to exist, and possibly for life's precursors to assemble. Thus, Earth during the bombardment was not permanently hostile, it was a world of cycles, swinging between devastation and habitability. Could life survive? Could life have existed during this cosmic onslaught? Some scientists argue that the bombardment would have sterilized the planet's surface repeatedly. Others suggest that life could have taken refuge underground, in hydrothermal vents, in deep crustal aquifers, or even inside impact craters where heat and chemistry created temporary safe havens. If life did begin during this time, it must have been tenacious, capable of surviving cycles of near annihilation. Lessons from other worlds. The bombardment was not unique to Earth. Mars, too, shows evidence of massive craters from this era. Venus and Mercury likely suffered as well, though their later geologies have obscured much of the record. But perhaps the most striking comparison is with the Moon. Its cratered face is a frozen snapshot of what Earth must once have looked like. Earth healed, recycled, and rebuilt itself, while the Moon kept its scars. The end of the storm. By around 3.8 billion years ago, the Great Bombardment tapered off. The inner solar system cleared of much of its debris, and impacts became less frequent. Earth at last entered a relatively calmer phase. Oceans stabilized, the crust thickened, and the atmosphere grew more consistent. And it was in this calmer aftermath, with oceans present, energy abundant, and raw materials supplied both by Earth and by space, that the stage was finally set for the origin of life. A turning point. The bombardment was both a crucible and a catalyst. Without it, Earth might have lacked the water and organics needed for life. With too much of it, Earth might never have cooled enough to allow life to begin. But in a narrow balance, Earth endured and emerged from the Hadean with oceans, continents, and chemistry ready for the next great step. The chemistry of life's dawn, prebiotic Earth and the first molecules, the storms had passed, the skies still bore scars, the oceans still trembled with heat, but Earth was quieter now than in its violent infancy. It was in this uneasy calm, between chaos and order, that a different kind of drama began, not of fire and stone, but of molecules. Here, on this battered young world, the earliest whispers of life began to stir. Earth, after the bombardment by about 3.8 to 4.0 billion years ago, the worst of the late heavy bombardment was ending. Earth had oceans once more, an atmosphere thick with gases, and land surfaces scattered as volcanic islands or proto-continents. The conditions were alien. Compared to modern Earth, atmosphere, lacked oxygen. Instead it was dominated by carbon dioxide, methane, ammonia, nitrogen, hydrogen, sulfide, and steam. Surface, crust was still thin and unstable, fractured by volcanoes and lava flows. Oceans, warm to hot, infused with minerals and gases, constantly churned by impacts and geothermal activity. It was an unstable, energy-rich environment, a perfect setting for prebiotic chemistry. The ingredients of life as we know it is built from just a handful of essential elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Together, these form the molecules that define living systems: amino acids, nucleotides, sugars, and lipids. Where did these building blocks come from? Volcanic outgassing. Volcanoes released carbon dioxide, methane, ammonia, and sulfur gases. Lightning storms and UV radiation energized these molecules into new compounds. Cometary and asteroidal delivery. Comets and carbon-rich asteroids delivered organic molecules, including amino acid precursors. Meteorites, like the meteorite, much younger, but a clue, contained dozens of amino acids, showing space can deliver life's raw materials. Hydrothermal vents. At the ocean floor, water interacted with volcanic rocks, producing hot, mineral-rich fluids. These vents provided energy gradients and chemical surfaces ideal for complex reactions. The Miller-Urey experiment in 1953. Scientists Stanley Miller and Harold Urey tested an idea: could life's building blocks form naturally in conditions similar to early Earth? They built an apparatus filled with gases thought to represent the early atmospheric methane, ammonia, hydrogen, and water vapor. They sparked it with electricity to mimic lightning. Within a week, the flask contained amino acids, the building blocks of proteins. This experiment showed that under the right conditions, simple chemicals could spontaneously assemble into molecules essential for life. Though we now know the early atmosphere may have been less reducing than Miller and Urey assumed, their work remains a landmark. It proved that life's chemistry is not miraculous, it is natural. Oceans as a chemical laboratory. The oceans of the Hadean and early Archean were vast laboratories where molecules collided, bonded, and broke apart endlessly. Shallow pools and tidal flats concentrated molecules as water evaporated, encouraging polymerization. Deep-sea hydrothermal vents provided constant heat, minerals, and gradients that fueled complex reactions. Mineral surfaces like clays and iron-sulfur crystals acted as catalysts, helping molecules link together. The ocean was not a passive backdrop, it was an engine of chemistry, churning with reactions that pushed molecules toward complexity. The RNA world hypothesis. One of the most compelling ideas about life's origins is the RNA world hypothesis. RNA, like DNA, can store genetic information. But unlike DNA, RNA can also act as a catalyst, folding into shapes that perform chemical reactions. This dual role means RNA could have been the first self-replicating molecule. In this scenario, simple organic molecules formed naturally in oceans and vents. These assembled into nucleotides, which linked into RNA strands. Some RNA strands began copying themselves, albeit imperfectly. Over time, this imperfect replication gave rise to evolution. The first life may not have been cells at all, but self-replicating RNA molecules floating in ancient seas. Competing theories. While the RNA world is influential, other theories also explore life's chemical beginnings. Metabolism. First hypothesis: life began as simple metabolic cycles on mineral surfaces before genetic molecules evolved. Iron-sulfur minerals at vents could have powered these cycles. Lipid world hypothesis: fatty acid molecules spontaneously form bubbles, protocells in water. These bubbles could trap molecules, creating microenvironments for chemistry to evolve. Clay hypothesis: clays can attract and arrange organic molecules, possibly guiding the assembly of polymers. Perhaps multiple pathways worked together, converging into the first proto-life. Energy sources driving chemistry. Life needs energy. In the absence of biology, early Earth provided plenty of natural engines. Lightning storms flashed across volcanic skies. Solar ultraviolet light bombarded the surface. Geothermal heat boiled up from the crust. Impact shocks from asteroids generated intense bursts of pressure and heat. This abundance of energy created a constant push toward molecular experimentation. The first proto-cells. At some point, molecules crossed the threshold from chemistry to biology. This may have happened when fatty acids assembled into membranes, forming bubbles. RNA-like molecules became trapped inside. These primitive protocells could grow, divide, and carry information, though imperfectly. Such protocells were not alive as we define it today, but they were the first containers of evolving chemistry, the ancestors of all life. The fragile beginnings. Life's first sparks were fragile. Ultraviolet radiation, impacts, and unstable climates could easily destroy them, yet persistence mattered. With every setback came new opportunities for chemistry to restart, refine, and diversify. By the end of the Hadean and into the early Archean, life, or at least its molecular precursors, had likely taken hold. 6.10 From chemistry to biology. The transition from molecules to life is still one of science's deepest mysteries, but we know this much. The Hadean Earth provided all the raw ingredients. Energy and cycles of destruction and renewal pushed chemistry forward. Molecules began to assemble into self-organizing systems. From this crucible, somewhere in Earth's oceans, the first sparks of life flickered, and once life emerged, it never let go. The first microbial life, from chemistry to biology for hundreds of millions of years. Earth had been a stage for violent impacts, raging volcanoes, and endless chemical experiments in its oceans and atmosphere. Molecules had collided, broken, apart, and reorganized in countless ways. But eventually, something extraordinary happened. The first true living systems appeared. These were not animals, not plants, not even simple algae, but microbes, tiny single-celled organisms that would rule the planet for billions of years. What defines life? Before diving into the earliest life forms, we must ask, what does it mean to be alive? Scientists generally define life by several traits: organization, cells or compartments with internal order; metabolism, the ability to capture and use energy; growth and reproduction, the ability to make copies of oneself; response to environment, reacting to changes or stimuli; evolution, passing traits to the next generation with variation. The first microbes may not have looked like much, tiny specks invisible to the naked eye, but they met these requirements. When did life begin? Pinpointing life's origin is challenging. Fossils from the Hadean are scarce because Earth's crust was constantly recycled by impacts and tectonics. Yet, indirect evidence gives us clues. Isotopic evidence. 4.1 to 3.8 billion years ago, carbon isotopes in ancient zircon crystals suggest biological activity may have existed over 4 billion years ago. This is controversial but tantalizing. Life could have emerged surprisingly quickly after Earth stabilized. Microfossils 3.5 billion years ago in Western Australia's apex chert, scientists discovered structures resembling microbial filaments. Though debated, many accept these as among the oldest preserved evidence of life. Stromatolites 3.5 to 3.7 billion years ago, layered rock structures formed by microbial mats. These are strong, visible evidence that microbial communities were thriving by this time. So while the exact date is uncertain, life likely appeared sometime between 4.1 and 3.7 billion years ago. While within the late Hadean to early Archean, the first cells, the earliest organisms, were prokaryotic cells, similar to modern bacteria and archaea. They were incredibly simple compared to modern life, but they had the essential features: a cell membrane made of lipids, genetic material, probably RNA first, later DNA, ribosomes to build proteins, basic metabolic pathways for energy. These cells were tiny, but they carried the potential to evolve into everything that followed. How did they eat? Life cannot survive without energy. The first microbes had several possible ways to feed: chemotrophy, chemical-eating microbes at hydrothermal vents may have used iron, sulfur, or hydrogen as fuel. This is still common in modern deep-sea bacteria. Anaerobic metabolism with no oxygen in the atmosphere. Early life was strictly anaerobic. Instead of oxygen, They used other molecules like sulfur or carbon dioxide for metabolism. Photosynthesis. Later innovation. Primitive photosynthesis may have evolved early, but true oxygen-producing photosynthesis by cyanobacteria came later, around 2.5 to 3.0 billion years ago. At this stage, Earth's biosphere was a microscopic chemical world. Cells floating in the ocean, clinging to rocks, or thriving around volcanic vents. The first ecosystems even with only microbes. Ecosystems existed, hydrothermal vent communities, similar to today's black smoke events. Microbes clustered around hot mineral-rich fluids. These were perhaps Earth's first stable ecosystems. Surface microbial mats on shorelines and tidal flats. Mats of microbes formed slimy colonies, trapping sediments. Over time, these mats built up stromatolites, floating planktonic cells. Some microbes simply drifted in the oceans, living off dissolved nutrients. Though primitive, these microbial networks were the first web of life. The great microbial dominance for billions of years, longer than most people realize, microbes were the only life on Earth. From approximately 3.8 billion years ago to approximately 600 million years ago, microbes dominated completely. Larger multicellular life did not appear until much later. Every complex creature alive today traces its ancestry back to these tiny pioneers. This means microbes aren't just the first life, they are also the most successful life form in history. Microbial evolution. Early microbes evolved rapidly because short lifespans allowed fast replication. Mutation and variation introduced constant diversity. Natural selection rewarded any advantage in energy use or survival. Over time, this led to a wide variety of microbial lineages: heat-loving extrophiles, sulfur-eating chemotrophs, early photosynthesizers. These evolutionary steps set the stage for Earth's first biosphere. The fragility of early life. Despite their resilience, early microbes faced constant threats. Asteroid impacts could boil oceans and sterilize the surface. UV radiation scorched the planet without an ozone layer. Unstable climate meant massive swings in temperature and chemistry. Yet life survived. Some microbes likely found refuge underground or deep in oceans, shielded from the worst catastrophes. This resilience suggests that once life appeared, it was nearly impossible to extinguish completely. The beginning of biological even the simplest life began altering Earth. Microbes changed the chemistry of oceans by consuming and releasing gases. Early photosynthesizers eventually began producing oxygen, though it would take billions of years for levels to build up. Stromatolites began constructing visible structures that reshaped shorelines. Life was no longer just a passenger on Earth, it was becoming a planetary force. From chemistry to biology, the emergence of microbes marks a profound transition. Before Earth was shaped by physics, geology, and chemistry. After biology joined the mix, adding evolution, metabolism, and ecological interactions. From this point onward, life and Earth would be inseparably linked. The Hadean Eon, once a world of fire and chaos, had given way to the dawn of biology. Tiny microbes, barely noticeable in size, had transformed Earth forever. In the chapters ahead, we will explore how these microbes evolved further, how photosynthesis changed the atmosphere, and how the stage was set for complex life to eventually emerge. Microbes reshaped the planet. Early photosynthesis and the path to oxygen. The rise of the first microbes marked a turning point in Earth's story. No longer was the planet shaped only by volcanoes, impacts, and oceans. Now, living organisms began influencing the very chemistry of the air, the seas, and the rocks themselves. The most dramatic innovation of all was photosynthesis, a process that would eventually flood the planet with oxygen, paving the way for complex life. But in the Hadean and early Archean, this transformation was only beginning. Life before oxygen. When life first appeared, Earth's atmosphere was anoxic, meaning it had no free oxygen. Instead, the air was filled with carbon dioxide, CO, methane, Shane ammonia, NH, nitrogen, N, hydrogen, H2S. This mix would be toxic, but to the first microbes it was a chemical paradise. They thrived without oxygen, relying on chemical reactions that used sulfur, iron, or carbon compounds for energy. These anaerobic microbes dominated for hundreds of millions of years. The innovation of photosynthesis. At some point, microbes developed a new trick: photosynthesis, the ability to capture sunlight and use it to build organic molecules. Two main types appeared. Unoxygenic photosynthesis, first stage used light, but not water, relied on other compounds like Hydrogen sulfide, H's, produced sulfur instead of oxygen, still common today in certain bacteria. Oxygenic photosynthesis, revolutionary stage, evolved in cyanobacteria, used water HO as the electron donor, released oxygen gas O as a byproduct. This innovation was one of the most important events in Earth's history. Oxygen was a highly reactive molecule once released. It would change everything. 8.3 Cyanobacteria, Earth's first oxygen factories. Cyanobacteria, sometimes called blue-green algae, were the first organisms to perform true oxygenic photosynthesis. They appeared around 3.0 to 2.7 billion years ago, possibly earlier. They lived in shallow waters, forming slimy mats. Over time, their activity built layered structures called stromatolites. Cyanobacteria are still alive today, and continue to be some of the planet's most important oxygen producers. Oxygen's early fate: at first, the oxygen produced didn't accumulate in the air. Instead, it reacted with Earth's oceans and rocks, oxidizing iron. Oxygen combined with dissolved iron in seawater. This created layers of iron oxides that sank to the seafloor over millions of years. These formed banded iron formations, BIFs, striped rocks that are among the most important geological evidence of early oxygen. Absorbed by minerals, oxygen reacted with volcanic gases and surface rocks, binding tightly. This created rust-red soils and minerals. Only after these sinks were filled could oxygen begin to accumulate in the atmosphere. The slow march toward oxygenation. This process was not quick. For hundreds of millions of years, oxygen production was balanced by oxygen consumption. The atmosphere remained low in perhaps less than 0.001% of today's levels. Oceans were mostly reducing environments, filled with iron and sulfur. Microbes lived in isolated niches, often competing fiercely. Yet, gradually, the balance tipped. By around 2.4 billion years ago, oxygen began to break free of the oceans. Chemical sinks. This moment would later trigger the Great Oxidation Event. Microbial impact beyond oxygen. Even before oxygen dominated, microbes were already reshaping the planet in other ways. Methane production. Some microbes, called methanogens, produced methane as a byproduct. Methane trapped heat in the atmosphere, helping to keep early Earth warm under a faint young sun. Carbon cycling microbes drew down carbon dioxide from the air, storing it in organic matter and rocks. Sulfur and nitrogen cycles. Microbial metabolisms began cycling sulfur and nitrogen through the biosphere for the first time. Earth's climate and atmosphere were linked directly to the actions of living organisms. The first crisis. Oxygen. As a poison. Ironically, oxygen was not initially a gift. It was a toxin to most early microbes. Oxygen is highly reactive and damages delicate biological molecules. Many anaerobic organisms were poisoned as oxygen levels rose. This led to the first mass extinction in Earth's history, wiping out countless microbial lineages. Yet, this crisis also created opportunity. Life that adapted to oxygen metabolism gained a powerful advantage. Evolution of aerobic respiration. Some microbes evolved ways to use oxygen instead of avoiding it. Oxygen allows much more efficient energy production than anaerobic methods. Aerobic respiration releases far more ATP, the energy currency of cells. This innovation gave oxygen-tolerant microbes a competitive edge. This evolutionary leap set the stage for complex multicellular life billions of years later. Microbes as planetary engineers. By inventing photosynthesis and oxygen production, microbes became the planet's first ecosystem engineers. They transformed the oceans by removing iron and sulfur. They transformed the atmosphere by adding oxygen and reducing greenhouse gases. They even altered geology, leaving behind mineral deposits and stromatolite reefs. From this point forward, Earth's surface and life were locked in a feedback loop, each shaping the other. Prelude to the Great Oxidation Event. The slow rise of oxygen during the late Hadean and Archean was just the beginning. Eventually, the sinks would be saturated, and oxygen would burst into the atmosphere in massive quantities. This event, the Great Oxidation Event, around 2.4 billion years ago, would mark the end of Earth's truly alien environment. But in the Hadean and early Archean, the seeds of that revolution were only being planted. From invisible microbes drifting in shallow seas, the Earth began its first great transformation. Life had gone from a passive passenger to an active shaper of the planet. The path toward an oxygen-rich world had begun, setting the stage for new evolutionary possibilities. In the next chapter, we will explore the Great Oxidation Event itself, the first planetary catastrophe caused by life. The Great Oxidation Event, Earth's first mass extinction, setting the stage for hundreds of millions of years. Earth was ruled by microbes in an oxygen-free world. Cyanobacteria had begun producing oxygen through photosynthesis, but that oxygen was immediately consumed by chemical reactions. It rusted iron in the oceans. It reacted with volcanic gases. It was absorbed by minerals in rocks. For a long time, oxygen levels in the air barely budged. The atmosphere remained dominated by carbon dioxide, methane, and nitrogen. But around 2.4 billion years ago, the balance shifted. Earth's chemical sponges could no longer soak up all the oxygen. What was once rare began to accumulate. This moment is known as the Great Oxidation Event (GO), a turning point in Earth's history. The oxygen flood once oxygen began escaping into the air. The transformation was rapid on a geological timescale. Oxygen levels in the atmosphere rose from near zero to perhaps 1 to 10% of today's levels. This was still far below modern oxygen concentrations, but it was revolutionary. The skies, once orange with methane haze, gradually turned blue. Ozone OV, formed from oxygen, began to collect in the upper atmosphere, shielding the surface from deadly ultraviolet radiation. For the first time, the Earth's surface became a place where complex chemistry and eventually complex life could unfold. Catastrophe for anaerobes. For the dominant microbes of the time, oxygen was not a blessing, it was a poison. Oxygen molecules react aggressively with cell components, damaging proteins, lipids, and DNA. Entire ecosystems of anaerobic microbes began to collapse. Species that had thrived for billions of years suddenly found their habitats shrinking. This event is sometimes called Earth's first mass extinction. It wiped out countless microbial lineages, leaving behind only those able to hide in oxygen-free niches such as deep sediments, hydrothermal vents, or the guts of future animals. Some of these anaerobes survive even today, as living relics of a pre-oxygen world. The disappearance of methane and the first global glaciation. Oxygen didn't just poison life, it also changed the climate. Before the GO, methane produced by microbes was a powerful greenhouse gas. When oxygen levels rose, oxygen combined with methane, breaking it down into carbon dioxide and water. CO is also a greenhouse gas, but far weaker than methane. Result: a dramatic cooling of the planet. Geological evidence suggests that soon after the GOE, Earth may have plunged into one of its first great global glaciations, possibly even a snowball Earth, where ice spread nearly to the equator. This icy catastrophe may have lasted millions of years, testing the survival of early life. Banded iron formations. The red rocks of oxygen. One of the most striking legacies of the GOE lies in the rocks themselves. As oxygen built up in the oceans, it continued to react with dissolved iron. This process deposited massive amounts of iron oxides on the seafloor. The result was banded iron formations, BIFs, layered rocks of alternating, iron-rich and silica-rich material. These formations are found worldwide today, from Australia to Canada to Africa. They are not just geological curiosities, they are a record of Earth's transition from an anoxic to an oxygenated world. The dawn of aerobic life. While most microbes perished, some adapted. A few lineages evolved ways to tolerate oxygen, and eventually, they learned to use oxygen in their metabolism through aerobic respiration. This process was far more efficient than anaerobic energy production, yielding up to 18 times more energy per molecule of glucose. This innovation gave survivors a huge evolutionary advantage. These aerobic microbes would later become the ancestors of all complex multicellular life. Geological consequences. The GO did more than change life, it transformed Earth's very geology. Oxidized minerals appeared for the first time. Rocks turned red as iron-rich soils and sediments rusted. Sulfur cycles changed, as oxygen altered the chemistry of volcanic gases. Atmospheric chemistry shifted toward stability, with ozone beginning to shield Earth's surface from harmful UV radiation. The GO marked the end of the truly alien Earth and the beginning of a planet more familiar to us. A double-edged sword. The Great Oxidation Event was both a catastrophe and an opportunity. Catastrophe: it drove countless species to extinction, poisoned the seas, and triggered glaciation. Opportunity: it cleared the way for new forms of metabolism, more energy-rich life, and ultimately, the rise of complexity. In hindsight, it was one of the most important evolutionary bottlenecks in history. Without it, humans and nearly all modern life would not exist. Oxygen as a planetary engineer. From this point onward, oxygen would be a permanent fixture of Earth's environment. It paved the way for the eventual explosion of multicellular life. It stabilized the climate in the long run despite short-term ice ages. It forever linked biology and geology in a feedback loop. The Go shows us how life is not just a passenger on Earth, it is a driver of planetary change. Legacy of the first extinction. Though the GOE happened billions of years ago, its fingerprints remain everywhere, in the rocks we mine for iron, in the oxygen we breathe today, in the very possibility of complex life. It was a moment when the planet was nearly destroyed, but also reborn. The Earth of the Hadean and early Archean was gone forever. A new Earth had emerged, one with oxygen, blue skies, and the promise of evolution's next chapters. From death came opportunity, and from poison came progress. The Great Oxidation Event reshaped the planet, leaving a world forever changed. In the next chapter, we will explore how Earth, recovering from ice ages and extinctions, prepared the stage for the rise of continents, stable climates, and the first stirrings of truly complex life. The stabilization of continents and the rise of early supercontinents. The Earth after the Great Oxidation. The Great Oxidation Event had forever altered Earth's environment. Oceans froze, methane dwindled, oxygen rose, and countless species were driven to extinction. Yet in the aftermath of this upheaval, Earth began to find a new equilibrium. For the first time in its history, Earth's surface started to resemble the world we know today. Stable landmasses that resisted erosion. A hydrological cycle shaped by rainfall, rivers, and oceans. An atmosphere increasingly buffered by oxygen and nitrogen. This was the stage on which the first supercontinents would appear. The growth of continental crustally continental crust had been fragile during the Hadean and early Archean protocontinent, where thin easily recycled back into the mantle, fragmented into island arcs and small cratons, ancient continental cores. But as Earth cooled, continental crust thickened. Granitic rocks, lighter than basaltic seafloor, began to float more securely atop the mantle. These stable blocks, called cratons, became the seeds of continents. Cratons formed the nuclei of modern continents and are among the oldest rocks we know. Some, like those in Western Australia, Greenland, and South Africa, are more than 3.5 billion years old. From cratons to continents once formed, cratons didn't remain isolated. Through the endless motions of plate tectonics they collided, sutured, and grew. Island arcs merged into larger landmasses. Volcanism and subduction added new material. Mountain building events, orogenies, stabilized the growing continents. By around 2.0 to 2.5 billion years ago, the Earth's surface was no longer dominated by scattered volcanic islands. Instead, vast continental shields had emerged, foundations of the continents we walk on today. The birth of supercontinents. A true hallmark of Earth's maturing geology was the supercontinent cycle. Supercontinents are massive landmasses formed when most or all of Earth's continents assemble into one. They do not last forever. Instead, they form, break apart, and reform over hundreds of millions of years. The earliest known supercontinent was likely Kenneland, 2.7 billion years ago. Some geologists also propose an earlier one, approximately 3.0 billion years ago, smaller and less global in scale. Kenneland's assembly was a milestone. It showed that Earth's lithosphere had cooled and strengthened enough to allow massive, long-lived continents. Climate and supercontinents profoundly influence climate. Large landmasses alter ocean circulation and wind patterns. They create vast interiors with extreme climate, scorching summers and freezing winters. Their breakup and assembly drive cycles of greenhouse and icehouse conditions. Kenneland's breakup may have been linked to another great glaciation. As rifting tore the landmass apart, volcanic gases and changing ocean circulation shifted the balance of greenhouse gases, pushing Earth once more toward an icy state. Oxygen, weathering, and soil. With large continents came vast surfaces exposed to weathering. Rainwater, slightly acidic due to carbon dioxide, reacted with continental rocks. These reactions drew down atmospheric CO, regulating Earth's climate. Weathering also delivered nutrients, phosphorus, iron, and trace metals. Rivers and oceans. This nutrient supply was critical for sustaining microbial life, especially photosynthetic. In turn, these organisms continued to pump oxygen into the atmosphere. Thus, the growth of continents and the spread of soils were tied directly to the evolution of Earth's atmosphere and biosphere. The first modern tectonics by the Hadean Era, approximately 2.5 to 1.6 billion years ago. Plate tectonics operated in a manner similar to today. subduction zones recycled ocean crust, mountain ranges rose where continents collided, rift valleys opened and closed with the movement of plates. This was a major turning point. Earth had moved beyond its chaotic, molten youth into a dynamic yet stable system, a planet capable of sustaining life for billions of years to come. The hidden legacy in today's cratons. Even now, the scars of these ancient processes remain: the Canadian Shield, the Pilbara Craton in Australia, the Kopfol Craton in South Africa. These ancient rocks are survivors from the Archean and Paleoproterozoic, silent witnesses to the time when Earth's first continents rose from the seas. Supercontinents as engines of evolution. The assembly and breakup of supercontinents did more than shape the land. They were engines of biological innovation. Mountain building created shallow seas, perfect habitats for microbial life. Erosion released nutrients into oceans, driving photosynthesis. Volcanism and rifting altered atmospheric gases, forcing life to adapt. Every cycle of supercontinent formation and destruction would test life's resilience and prepare the way for more complexity. A world preparing for complexity. By the close of the Paleoproterozoic, Earth was no longer the alien planet of the Hadean or Archean. It had continents, mountains, and stable crust. It had weather systems and rainfall cycles much like today. It had oceans teeming with microbial life. It had an atmosphere with oxygen, albeit far below modern levels. The planet was still far from the lush world of animals and forests, but the stage was being set. The rise of supercontinents was not just a geological story. It was part of the long preparation for the greatest evolutionary leap in history, the emergence of complex, multicellular life. The Earth had survived fire, ice, and poison. Now it stood as a planet with land, seas, and sky in balance. In the next chapter, we will journey into the Mesoproterozoic era, often called the Boring Billion, a time that seemed uneventful, but quietly laid the foundation for the explosion of complexity to come. The Boring Billion, a long quiet before the storm, the calm after chaos after billions of years of upheaval, asteroid impacts, magma oceans, global glaciations, and the great oxidation. Earth entered what scientists call the Mesozoic Era, spanning almost a billion years from about 1.8 to 0.8 billion years ago. It is sometimes nicknamed the Boring Billion because fewer catastrophic events occurred compared to earlier eons. Evolution seemed to slow, with microbial life dominating. Climate and atmosphere remained relatively stable, but this era was far from truly boring. Beneath the surface, the planet was laying the groundwork for the rise of complex life. The assembly of Nuna Columbia at the dawn of the Mesoproterozoic, Earth's continents gathered into a vast supercontinent called Nuna, also known as Columbia, formed around 1.8 billion years ago, stretched across much of the globe, uniting cratons from North America, Asia, and beyond, created mountain ranges and continental interiors that stabilized Earth's crust. This stability reduced the frequency of massive volcanic events and helped moderate climate cycles. A billion years of geological stability for nearly a billion years. Nunan later, its successor Rodinia, dominated Earth's surface. Plate tectonics continued, but on a slower, grander scale. Oceans expanded and contracted around the supercontinents. Subduction zones recycled crust steadily, without cataclysmic upheaval. Erosion of the vast continental interiors supplied steady nutrients to the oceans. This geologic calm allowed Earth's biosphere to settle into a slow, steady rhythm. Oceans of microbes. During this time, Earth's oceans remained the domain of prokaryotes. Bacteria and archaea, cyanobacteria, still carried out photosynthesis, releasing oxygen. Stromatolites, layered microbial mats, thrived in shallow seas. Sulfur and iron metabolizing bacteria dominated deeper waters. The lack of predators meant microbial communities flourished with little evolutionary pressure to change. This gave rise to the impression of evolutionary stagnation, but in reality, small, crucial innovations were occurring quietly. Oxygen plateau. The great puzzle, though, the great oxidation event had raised oxygen levels. They did not immediately rise to modern concentrations. For most of the Mesoproterozoic, oxygen levels plateaued at only 1 to 10% of today's atmosphere. This was enough to support microbial diversity, but not yet enough for complex animals. Scientists believe this oxygen ceiling was maintained by a balance between photosynthetic oxygen production and its consumption by volcanic gases and organic decay. Thus, Earth lingered in a state of dynamic balance. Early eukaryotes, the first complex cells hidden within this billion years of microbial com, was a revolution, the rise of the first eukaryotic cells. Unlike simpler bacteria, eukaryotes contained nuclei to house DNA, mitochondria, which generated efficient energy through respiration, internal membranes that organized cell functions. Fossil evidence suggests eukaryotes first appeared around 1.6 to 1.8 billion years ago. These cells were much larger and more complex than bacteria. They represented the blueprint of all future complex life: plants, animals, fungi, and humans. Rodinia, the next supercontinent around 1.1 billion years ago, Nuna had broken apart and reassembled into another great supercontinent. Rodinia likely stretched from pole to pole. Its vast interiors were arid and extreme in temperature. Its coastlines supported thriving microbial mats and cstromatiolites. The assembly of Rodinia also brought new cycles of mountain building, erosion, and nutrient delivery to the oceans, subtly fueling biological changes. Glimpses of multicellular richly life remained dominated by microbes. Signs of multicellularity began to emerge. Simple colonies of cells began cooperating. Some algae developed differentiated structures. Fossils suggest that multicellular red algae may have appeared as early as 1.6 billion years ago. These were tiny, tentative steps, but they were the first cracks in the microbial monopoly. Why was it boring? Scientists once called this period boring because it lacked dramatic events, but research now shows it was anything but dull. Stable tectonics allowed the long-term buildup of oxygen and nutrients. Eukaryotes quietly diversified, though not explosively. Continental weathering slowly reshaped Earth's atmosphere. The Mesoproterozoic may have seemed uneventful, but it was a time of preparation, a billion-year-long balancing act that made the later rise of animals possible. The storm to come as the Mesoproterozoic drew to a close around 800 million years ago. Rodinia began to rift apart. Vast volcanic activity released greenhouse gases. Continental breakup shifted ocean currents. Climate entered a new era of extremes. What followed was anything but boring. The Cryogenian period, with its snowball Earth glaciations, and eventually the Ediacaran period, when the first large, complex organisms appeared. The boring billion was not a wasted era, it was Earth's long rehearsal, a billion-year breath before the crescendo of complexity. In the next chapter, we will enter one of the most dramatic and mysterious times in Earth's history, the Cryogenian period, when the planet may have frozen from pole to pole. Snowball Earth, the planet that froze over a world on the brink of extremes by the end of the Mesozoic. Earth's stability began to unravel. The breakup of the supercontinent Rodinia reshaped oceans and atmosphere. Vast volcanic rifts opened, spewing gases into the sky. Continents shifted toward the equator, altering climate dynamics. Weathering of the continental crust drew down atmospheric carbon dioxide. The balance tipped. Earth's thermostat plunged into its coldest setting yet. What followed was the Cryogenian period, a time of unimaginable planetary transformation. The hypothesis of a frozen globe. Geologists studying ancient rocks discovered puzzling evidence. Glacial deposits found near the equator. Dropstones, large rocks carried by icebergs embedded in ancient marine sediments. Global layers of carbonate rock called cap carbonates lying directly atop glacial layers, hinting at sudden, massive warming events. These clues gave rise to the Snowball Earth hypothesis. At least twice during the Hadean Eon, the entire planet was covered in ice. The Sturtian glaciation, approximately 720 to 660 million years ago. The Maronan glaciation, 650635 million years ago. During these frozen intervals, Earth may have looked like a pale, shimmering marble spinning in space. The ice advanced. How could Earth freeze over so completely? As Rodinia broke apart, more landmass sat at tropical latitudes. Intense weathering of these rocks pulled CO out of the atmosphere. Lower greenhouse gas levels allowed global cooling. Ice sheets advanced toward the equator. Once ice reached low latitudes, its bright, reflective surface amplified cooling, a runaway feedback loop that encased the globe in ice. Life under the ice. A frozen Earth seems incompatible with survival, yet life endured. Scientists believe microbial life found refuge in hydrothermal vents on the ocean floor, where heat and chemicals sustained chemosynthetic bacteria. Thin patches of open water near volcanic islands, subglacial lakes beneath thick ice sheets, photosynthetic pockets and thin films of water beneath sea ice are far from annihilated. Microbial ecosystems persisted and possibly innovated. A world of white silence. Earth in the depths of the Maronan glaciation, oceans sealed under kilometers of ice, continents buried beneath glaciers stretching into the tropics. Temperatures plummeting to -50 degrees Celsius in equatorial regions. Atmospheric circulation altered, with weak winds and reduced rainfall. The world was a silent, frozen tomb. Yet beneath the ice, microbial metabolisms quietly ticked on, like embers waiting for oxygen. Volcanic rescue. The greenhouse rebound. If Earth was locked in ice, what melted it? Volcanic eruptions continued even in a frozen world, with silicate weathering. Suppressed by ice cover, carbon dioxide from volcanoes built up unchecked in the atmosphere. Over millions of years, CO levels may have risen to hundreds of times modern levels. At last, the greenhouse effect overwhelmed the icy grip. Glaciers retreated. Oceans roared back to liquid. Cap carbonates, the geological signature, the rapid, knelt left behind one of geology's most striking signatures. Thick layers of carbonate rock formed as CO-rich oceans precipitated minerals. These cap carbonates blanket glacial deposits worldwide. They are Earth's geological scar, proof of a planet that froze, then thawed in a cataclysmic swing. Biological consequences. The Snowball Earth episodes were more than climate curiosities, they were evolutionary crucibles. The stress of survival may have pushed microbes to experiment with new strategies, including multicellularity. After the Maronan thaw, oxygen levels rose dramatically. Eukaryotic algae expanded across oceans, enriching ecosystems with more complex food webs. In the wake of global ice, the seeds of complex life were sown. The shattered silence. By about 635 million years ago, the Maronan glaciation ended. Earth warmed, oceans turned green with algal blooms, and oxygen surged. The stage was set for a biological revolution within a few tens of millions of years. The first large, soft-bodied organisms would emerge, the mysterious precursors to animals. Snowball Earth had nearly destroyed life, but instead, it sharpened its resilience. Out of ice came innovation. Out of silence came complexity. The paradox of ice and life. The Snowball Earth remains one of the most intriguing paradoxes in science. How did life survive global glaciation? Did these frozen episodes accelerate evolution, or delay it? Could such events occur on exoplanets orbiting other stars? What we do know is this: without Snowball Earth, the rise of animals and eventually humans might never have occurred. The cryogenian was Earth's ultimate trial by ice. Yet from the crucible of glaciers, life emerged stronger. In the next chapter we will witness the dawn of something unprecedented, the rise of the first complex, macroscopic organisms in the Ediacaran period, the true dawn of animals. The Cambrian explosion, life's Big Bang. The stage is set. The Cambrian period began around 541 million years ago. Following the mysterious disappearance of the Ediacaran biota. Earth was ready for change. Oxygen levels had reached new highs. The climate was relatively stable, with warm shallow seas covering vast areas of continental shelf. Nutrients from weathered rocks enriched the oceans, fueling food webs. It was a world ripe for innovation. What followed was an evolutionary detonation. What was the Cambrian explosion? The Cambrian explosion refers to a geologically rapid diversification of life between 541 and 520 million years ago. Nearly every major animal body plan phylum emerged during this time. Hard parts like shells, spines, and exoskeletons appeared for the first time. Predation, burrowing, swimming, and complex ecosystems developed in less than 20 million years. In evolutionary terms, this was an instant burst of creativity after billions of years of microbial dominance. The evolution of hard parts. Of the most important innovations was biomineralization, the ability to form hard skeletons. Calcium carbonate and calcium phosphate were used to build shells, teeth, and protective armor. Fossils suddenly became far more abundant and diverse. Hard skeletons provided protection against predators and structural support for movement. The Cambrian marks the first true fossil-rich period of Earth's history. The arms race begins. With hard parts came predation, and with predation came an evolutionary arms race. Predators developed claws, teeth, and speed. Prey evolved shells, spines, burrowing behavior, and camouflage. This ecological feedback loop accelerated diversification. For the first time, life was not just existing, it was competing, hunting, and defending the Cambrian ecosystem. The seas of the Cambrian swarmed with new life forms, trilobites, armored arthropods, scuttling across seafloors, becoming one of the most iconic fossils of the Paleozoic. Anomalocaris, giant predators, up to 1 meter long, with grasping appendages and a circular mouth lined with teeth. Opabenia, a bizarre creature with 5 eyes and a trunk like proboscis. Wewaxia, slug-like, covered in protective spines. Hallucigenia, a worm-like animal with spines on its back and clawed legs. So strange it baffled paleontologists for decades. This was an ecosystem of novelty animals experimenting with form and function. The role of oxygen in chemistry. Why did this explosion happen now? Several factors converged. Rising oxygen levels supported larger, more active animals. Nutrient-rich seas from weathering fueled plankton growth. Expanding food webs. Genetic innovation. The evolution of developmental toolkits like Hoxgene allowed organisms to build complex, segmented bodies together. These set the stage for evolutionary creativity on a grand scale. Burrowing and the agronomic revolution. Another key Cambrian innovation was burrowing behavior. Before the Cambrian, most organisms lived on top of microbial mats. During the explosion, animals began burrowing into sediments, disrupting seafloor communities. This re-engineered ecosystems, oxygenating the seafloor and opening new habitats. The agronomic revolution transformed the seafloor into a dynamic, living environment. Burgess Shale, a window into the explosion. One of the most important fossil sites for Cambrian life is the Burgess Shale in Canada. It preserves delicate soft-bodied organisms in stunning detail. Creatures like Hallucigenia, Opabenia, and Anomalocaris are known largely from this site. The Burgess Shale reveals just how strange and experimental Cambrian life truly was. Other important Cambrian fossil sites include Chenjung in China and Sirius Passet in Greenland. The birth of modern animal groups. Almost all major modern phyla trace their roots back to the Cambrian. Arthropods, insects, spiders, crustaceans, mollusks, snails, clams, octopuses, chordates, fish, and eventually vertebrates like us. Echinoderms, starfish, sea urchins. This was the evolutionary blueprint of the modern biosphere. Why the Cambrian matters. The Cambrian explosion marks a fundamental turning point. Before, Earth was dominated by microbes and simple multicellular life. After complex ecosystems with predators, prey, and trophic webs defined the biosphere. It was life's first golden age of complexity. Without it, the path to fish, amphibians, reptiles, mammals, and humans would not exist. A short, brilliant firework. Despite its brilliance, the Cambrian was relatively brief. By 485 million years ago, the Cambrian period ended, giving way to the Ordovician ecosystem stabilized and biodiversity continued to expand. The Cambrian was a spark, a sudden ignition of diversity, but it was the Ordovician and beyond that nurtured this spark into the vast tree of life we know today. The Cambrian explosion was not just an event in evolution, it was the foundation of modern animal life. From armored trilobites to bizarre, five-eyed predators, it was a world of experimentation, survival, and innovation. In the next chapter, we will explore how this evolutionary firework transitioned into the Ordovician period, where life continued to expand, colonizing new environments, and growing into ecosystems of greater stability and richness. The Ordovician, oceans of life expanding biodiversity. The Cambrian explosion had set life on an unprecedented trajectory, but the Ordovician period 4854 for 3 million years ago marked a profound expansion. Earth's oceans became a canvas of ecological diversity. Shallow seas covered large continental shelves, creating ideal habitats for marine organisms to flourish. Brachiopods and bryozoans formed dense colonies, anchoring themselves to the seafloor. Mollusks, including the earliest nautiloids, glided through the oceans, hunting for food and evading predators. The first jawless fish primitive vertebrates began exploring the marine waters, setting the stage for future evolutionary leaps. The oceans were no longer dominated by small, simple creatures. Complex communities thrived, with intricate predator-prey relationships shaping the dynamics of life. Colonization of ecological niches. During the Ordovician, life explored new strategies for survival. Organisms began burrowing into sediments, creating underground habitats. These behaviors, increased oxygen penetration into the seafloor, allowed small organisms to evade predators, created new ecological niches, encouraging diversification. Meanwhile, plankton blooms increased the availability of nutrients. This fueled larger food chains, with filter-feeding organisms dominating some environments while predatory nautiloids and other early predators hunted in open waters. The Ordovician seas were vibrant, teeming with life in ways never seen before. End Ordovician extinction. Despite thriving ecosystems, the Ordovician period ended with a catastrophic glaciation event. Glaciers advanced, lowering sea levels and reducing shallow marine habitats. Temperature fluctuations stressed marine life, leading to the first major mass extinction, where nearly 85% of marine species vanished. Yet, extinction also allowed for evolution's next chapter. The survivors adapted and diversified, preparing Earth for the Silurian period, where life would expand into new ecological and geographic territories. Silurian and Devonian. Life moves ashore. Silurian sees the Silurian period 443419 million years ago marked a time of recovery and expansion after the Ordovician. The oceans became more stable, and shallow tropical seas spread across the continents. Coral reefs began forming, creating the first permanent underwater ecosystems. Brachiopods, mollusks, and crinoids flourished in these reefs, providing food and shelter for countless organisms. Early jawless fish evolved further, some developing rudimentary fins for better mobility. These reefs and seafloors were the first signs of structured, complex marine ecosystems, where species interacted in new and dynamic ways. Devonian, the age of fishes. The Devonian period, 419 to 359 million years ago, is often called the age of fishes, because of the incredible diversification of aquatic vertebrates. Jawed fish appeared, including early sharks and bony fish, giving predators a new edge. Lobe-finned fish evolved, possessing fleshy fins with bones that would eventually allow vertebrates to venture onto land. Oceans were teeming with diverse species, from armored placoderms to small, agile fish hunting plankton. The Devonian seas were alive with experimentation. Predation, schooling, and defense mechanisms became more sophisticated, shaping evolution in ways that would influence all vertebrates. First land, plants and land. A quiet revolution was unfolding. Simple plants had emerged during the Silurian, but in the Devonian, vegetation began colonizing the continents more extensively. Early vascular plants developed, allowing them to transport water and nutrients efficiently. Plants began forming, the first primitive forests, stabilizing soil and enriching the atmosphere with oxygen. Mosses, liverworts, and early ferns began creating habitats for invertebrates and setting the stage for terrestrial ecosystems. The arrival of plants on land was not just botanically, it reshaped the planet's climate, soil composition, and future evolutionary potential. First land, animals. The Devonian also saw the first true steps of animals onto land. Small arthropods, such as millipede-like creatures, explored the moist surfaces of emerging forests. The first tetrapods evolved from lobe-finned fish, venturing onto land for short periods, perhaps hunting or escaping predators. This was a pivotal moment. Life was no longer confined to water. The Earth's continents became a new frontier, and organisms began experimenting with locomotion, breathing, and reproduction in terrestrial environments, shaping Earth's future. By the end of the Devonian, Earth had changed profoundly. Oceans were filled with diverse vertebrates and invertebrates. Land was slowly greening, forming ecosystems that could support animals. oxygen levels continued to rise, allowing larger, more complex life forms to develop. Yet, the Devonian was also a time of extinction and turnover. Climate fluctuations, sea level changes, and localized anoxia led to several extinction pulses. These challenges would shape the resilience and adaptability of terrestrial and marine life alike. The Silurian and Devonian were an age of exploration, innovation, and firsts. Coral reefs, diverse fish, primitive forests, and the first animals crawling onto land. These chapters laid the foundation for Earth's next great era, where forests and giant insects would dominate the Carboniferous period. Carboniferous, forests and giant insects, lush tropical forests. The Carboniferous period, 359 to 299 million years ago, was a world dominated by dense tropical forests and swamps. Vast wetlands and rivers crisscrossed the continents, creating perfect conditions for lush vegetation. Giant ferns, horsetails, clubmosses, and towering primitive trees formed immense forests, some reaching heights of over 30 meters. These forests played a crucial role in reshaping the atmosphere, absorbing carbon dioxide and releasing oxygen. The Carboniferous is often remembered as a green world, where plant life transformed the planet, setting the stage for future terrestrial ecosystems. Giant insects and early reptiles. The high oxygen levels during the Carboniferous allowed insects and other arthropods to grow to enormous sizes. Dragonflies with wingspans of over 70 centimeters patrolled the swampy skies. Millipedes, centipedes, and other arthropods grew larger than anything alive today. Meanwhile, vertebrates were evolving. Early amniotes, primitive reptiles, appeared, laying eggs on land, a revolutionary adaptation that freed animals from dependence. On-water amphibians thrived in swampy habitats, reaching lengths of several meters in some cases. These developments marked the first true dominance of terrestrial ecosystems, where animals and plants were increasingly intertwined. Coal formation. One of the Carboniferous' most important legacies is the formation of vast coal deposits. Swamp forests produced thick layers of plant material that did not fully decompose in waterlogged conditions. Over millions of years, this plant matter transformed into coal, providing an enduring record of Carboniferous forests. These coal beds would later fuel human industrialization, linking deep time to modern civilization. The Carboniferous forests were not just biologically significant, they literally shaped the planet's geology. Shaping the atmosphere. Oxygen levels during the Carboniferous reached up to 35%, far higher than today's 21%. This allowed larger body sizes in insects and amphibians. High oxygen also influenced fire patterns, with occasional natural wildfires spreading across dry forest floors, maintaining ecological balance. The Carboniferous period represents a golden age of terrestrial life, where ecosystems matured and species explored new biological possibilities. Transition to the Permian. By the end of the Carboniferous, continental movements began forming the supercontinent Pangaea, altering climate and ocean circulation. Swamps receded as drier climates emerged. Amphibians and early reptiles adapted to these changes, setting the stage for the Permian period, where life would face the greatest challenge yet, the largest mass extinction in Earth's history. Carboniferous was a world of greenery, oxygen-rich air, and giant creatures. Forests and swamps flourished, insects and amphibians thrived, and life on land reached new heights both literally and figuratively. This period set the stage for the rise of complex terrestrial ecosystems and the dramatic events of the Permian. The rise and fall of early complex ecosystems. 18.1 Supercontinent Pangaea. By the Permian period, 299 to 252 million years ago, Earth's continents had merged into a single massive landmass called Pangaea. This supercontinent dramatically altered climate patterns and ocean currents. Interior regions became dry and arid, while coastal areas remained wetter. Mountain building reshaped landscapes, creating new habitats for terrestrial life. Pangaea's formation set the stage for evolutionary challenges, pushing life to adapt to increasingly extreme conditions. 18.2 Diverse terrestrial life. The Permian marked the rise of more advanced terrestrial ecosystems. Early reptiles diversified, developing adaptations to drier environments. Amphibians remained prominent in swamps and rivers but faced competition from evolving reptiles. Insects continued to thrive, exploiting forests and early seed plants. These ecosystems were highly structured, with complex food webs that reflected a balance between predators, prey, and vegetation. life was both flourishing and facing new pressures from environmental change. 18.3 Marine life in the Permian oceans were also diverse. Brachiopods, mollusks, and echinoderms were abundant on seafloors. Reef-building organisms, including sponges and corals, continued to shape marine habitats. Fish, including early sharks and bony fish, dominated the oceans as predators. Yet despite this richness, signs of ecological stress were emerging. Climate fluctuations and reduced shallow marine habitats foreshadowed a looming catastrophe. 18.4 The Great Permian Extinction. The Permian ended with the largest mass extinction in Earth's history. Around 252 million years ago, extensive volcanic eruptions in Siberia released enormous amounts of greenhouse gases. Oceans experienced widespread anoxia, oxygen depletion, killing many marine species. Over 90% of marine species and 70% of terrestrial species went extinct. This extinction event reshaped life on Earth, wiping out many dominant groups and opening ecological niches for the rise of the Mesozoic Era. 18.5 Legacy of the Permian. Though catastrophic, the Permian extinction had profound evolutionary consequences. Survivors, including early reptiles and synapsids, diversified in the Triassic, eventually leading to dinosaurs and mammals. Terrestrial and marine ecosystems were reorganized, allowing new forms of life to evolve. The Permian marks the end of Paleozoic dominance and sets the stage for the Mesozoic's age of reptiles. The Permian illustrates a critical truth about life on Earth. Extinction is not the end, it is a reset, a prelude to new evolutionary opportunities. From supercontinents to thriving ecosystems, from diverse marine life to the cataclysmic Permian extinction, this period embodies the resilience and adaptability of life. The Earth had endured fire, ice, and massive extinctions, yet life persisted, evolving in complexity and diversity, setting the stage for the rise of the dinosaurs and eventually, the world we inhabit today. Triassic, the dawn of dinosaurs. Life after the Permian extinction, the Triassic period to 5 to 201 million years ago, followed the greatest mass extinction in Earth's history. Life slowly recovered in both oceans and on land. Early reptiles and synapsids, survivors of the Permian, diversified to fill ecological niches. Shallow seas hosted recovering marine life, including ammonites and bivalves. This period set the stage for new evolutionary experiments, laying the foundation for the age of dinosaurs. Emergence of dinosaurs. Small, agile dinosaurs appeared during the mid-Triassic. Early species were often bipedal, carnivorous or omnivorous. Pterosaurs took to the skies, becoming the first vertebrate flyers. Though still small in number, these creatures foreshadowed a new dominant group that would rule terrestrial ecosystems for millions of years. Early mammals and synapsids. Mammal-like reptiles, synapsids survived the Permian extinction. The first true mammals appeared nocturnal and these early mammals coexisted with the emerging dinosaurs, quietly preparing for a future dominance long after the age of reptiles. Changing climate and geography. Pangaea remained largely intact, producing extreme seasonal climates. Volcanic activity in shifting continents created new habitats and microclimates. Life evolved rapidly in response to these environmental pressures, accelerating diversification. The Triassic marks the rebirth of ecosystems, with dinosaurs, early mammals, and plants exploring new forms and behaviors, setting the stage for the Jurassic, the age of giants, flourishing dinosaurs. The Jurassic period, 201 to 145 million years ago, was dominated by dinosaurs of all shapes and sizes. Massive sauropods roamed lush forests, feeding on abundant vegetation. Carnivorous theropods hunted in packs, evolving complex hunting strategies. Ornithischians developed armor and defensive adaptations, showcasing evolutionary innovation. Marine and aerial life. Oceans teemed with ichthyosaurs and ammonites. Pterosaurs ruled the skies, diversifying into many sizes and forms. Coral reefs and marine plants flourished, creating rich underwater ecosystems. First birds and advanced mammals. Early birds evolved from small theropod dinosaurs, adding flight to the ecosystem. Mammals remained small and nocturnal, diversifying quietly while dinosaurs dominated the day. Jurassic landscapes. Warm, humid climates supported vast coniferous forests and ferns. Rivers, lakes, and coastal plains provided diverse habitats for dinosaurs, mammals, and early birds. This era cemented the Mesozoic as the age of reptiles, showcasing evolutionary innovation on land, sea, and air. From fire to life, Earth's eternal story as we stand here in the present, gazing back across the 4.5 billion year history of our world. The story of Earth feels almost mythic. It began in fire. A molten planet, forged from cosmic collisions, shrouded in choking vapors and magma oceans. For hundreds of millions of years, Earth was more inferno than home. But from this chaos, order emerged. The crust cooled, water condensed, and the first oceans shimmered beneath alien skies. The Hadean Eon, once thought of as a hellish wasteland, was, in truth, the cradle of everything to come. Then came the first spark of life, in the hidden warmth of hydrothermal vents, or perhaps in shallow chemical-rich pools. Chemistry crossed the threshold into biology. Cells began their long experiment, multiplying, adapting, and surviving against a hostile planet. Through the endless expanse of the life remained microscopic, an invisible empire of bacteria, archaea, and algae. Yet these humble organisms reshaped the world. They split water with photosynthesis, releasing oxygen, rusting the very seas, and transforming the atmosphere. The Great Oxidation was not just a chemical event, it was the beginning of complex life's possibility. Then the stage widened. Eukaryotes emerged, carrying the power of mitochondria. Multicellularity blossomed, giving rise to strange forms, and at last, in the Cambrian, life exploded into complexity: hard shells, teeth, predators, prey. The seas swarmed with trilobites and molluscarids, and the ancestors of nearly every creature alive today. From fire to life, from simplicity to complexity, Earth had become more than a planet. It had become a living world, and yet this story is far from over. The Cambrian was only the opening act of animal evolution. The Ordovician seas, the Devonian forests, the age of reptiles, the rise of mammals, all these chapters were still waiting to be written. But in understanding Earth's beginnings, we understand something profound about ourselves. We are not separate from this story, we are its continuation. The iron in our blood was forged in ancient stars. The water we drink condensed from primordial steam. The cells that make up our bodies carry echoes of those first microbes in seas. That our world is ancient, our roots are deep, and our future, like our past, is tied inseparably to the rhythms of this remarkable planet. The Hadean may have been hell, but from that fire came the foundation of paradise.